Well, firstly, good afternoon. My name is Lucas Fonseca Caetano. I am a doctoral student at Universidade Federal de Ouro Preto. This research is named Influence of Exposed Steel Structure Area on the Thermal Performance of Artificially Conditioned Buildings. The increasingly common use of steel structures in commercial buildings leads to an increase in the complexity of design constraints. During the architectural design phase, the project should be defined more carefully, taking into account the energy efficiency of the building in accordance with the climatic conditions. In this context, simulation of the thermal behavior of buildings with the use of computer programs has generated several constructive advantages for the establishment of energy efficient buildings. When a high thermal conductivity material is placed in parallel with a less conductive material, or if the area of the exposed steel structure is large, most of the heat transfer occurs by conduction through the steel profile or exposed structure in an effect known as thermal bridge. This mechanism characterizes a reduction of the thermal resistance of the closure system, which causes an increase in energy costs for environment heating or cooling. So, in this context, this paper aims an analysis of the impact caused by an exposed steel structure area on the thermal performance of buildings, focusing on studying an artificially conditioned commercial building. The adopted method consists of numerical simulations using the Energy Plus program, version 8.6, which will predict the cooling thermal loads and the annual building electrical energy consumption. The building is simulated drawing directly the surfaces where the thermal bridges occur, considering two situations: building with the presence of exposed steel structure and building without the presence of exposed steel structure, replacing structural steel with a conventional closure system. The proposed model is a 10-floor building similar to commercial buildings typical of large urban centers, with two well-defined sectors: a vertical circulation, or core, and office space, as exemplified in Figure 1. The typical floor plan presented in Figure 1 was designed considering the structural system in reinforced concrete. Therefore, adaptations of the dimensions were made to adapt it to the system in steel structure, as shown in Figure 2. In any case, the model consists of five thermal zones: thermal zone 1 to 4, Z1, Z2, Z3, and Z4, as office areas, and thermal zone 5, Z5, as the central core or circulation zone, as is shown in Figure 3. In order to carry out the computational simulations, the Brazilian data of bioclimatic zoning provided by the Brazilian standard NBR 15220 are used as climatic references. The simulations are performed considering the cities of Curitiba, São Lourenço, São Paulo, Brasília, Vitória da Conquista, Campo Grande, Cuiabá, and Manaus as representative of bioclimatic zones 1, bioclimatic zone 2, bioclimatic zone 3, bioclimatic zone 4, bioclimatic zone 5, bioclimatic zone 6, 7, and bioclimatic zone 8 respectively. Following the recommendations of the Brazilian standard NBR 15575, some guidelines were adopted for the standardization of the computational simulations of the building: 2 ambient ventilation rates, 1 air change per hour and 5 air changes per hour; 3 solar radiation absorbance of the exposed surfaces: light color, absorptance 0.3, medium color, absorptance 0.5, and dark color, absorptance 0.7. Considering the analysis made for the typical summer design day, the Brazilian standard NBR 15575 recommends all Brazilian bioclimatic zones should be evaluated. It is defined as the standard of use the air conditioning operating from 8 a.m. to 6 p.m. and a control temperature of 24 degrees Celsius was adopted for the cooling function. Table 1 shows the total cooling thermal loads of the Zone 1, which represents the most critical case in increasing the thermal loads of the environments and the percentage of increase in thermal loads when comparing the influence of structural system in the results, considering steel profiles with web heights that range between 30 centimeters, 35 centimeters, and 40 centimeters. It was evaluated that, in the case of the representative city of Bioclimatic Zone 4, the total cooling thermal load of the environment increased more significantly, reaching a 10.6% increase considering steel profile with a 40 centimeters web height. Figure 4 shows a comparison of the evolution of cooling thermal load for the most critical case evaluated in the bioclimatic zone 4, considering 3 steel profiles evaluated. It was observed that comparing the extreme steel profiles, that's it, web heights 40 centimeters and 30 centimeters, there was an increase of about 2% in the total cooling thermal loads of the environments. Table 2 shows the influence of the steel structure on the electric energy consumption considering the evaluation for the typical summer design day. In general, the structural system is not considered in the simulations of the building's thermal performance. The results presented in Table 2 show that, for the study object of this work, the disregard of the structural system in exposed steel beams can lead to an increase in cooling energy consumption of up to 12.5% for the typical summer design day in the representative city of the bioclimatic zone 4. This increase in energy consumption was also very significant for all the bioclimatic zones evaluated. So, as conclusion, in this study, the influence of exposed steel structure area on the thermal performance of artificially conditioned commercial building was evaluated, considering a structural system with steel profiles and web heights varying between 30 centimeters, 35 centimeters, and 40 centimeters, disregarding the presence of internal heat sources. It was observed that the effects of thermal bridges were more evident in the evaluation made for bioclimatic zone 4. There was an increase of 10.6% in the total cooling thermal load considering beams with a 40 centimeter web height. As consequence, the consideration of the structural steel system in numerical simulations also increased the energy consumption, reaching a maximum increase value of 12.5% in the bioclimatic zone 4. These results cannot be expanded to other building types, since commercial buildings have their own characteristics such as wide and well-defined circulation areas, environments with high ceilings, light internal partitions, facades with large glass areas, and others. However, it was evident that in the structural design, the thermal behavior of the closure system as a whole should also be considered as a conditioning factor when choosing the structure. So, this study indicates that the steel structure should be considered in the early numerical simulation of the thermal performance of buildings, due to the effect of thermal bridges and the consequent increase in costs for cooling. Thank you for your attention.